close sound coming out.
Hi, my name is Darlington Etaje, and this is
Ashkari.
and they are,
My name is Ray Hulok. My name is Ainley.
and we are the Drillbotics Group A team of the University of Calgary, here to do our simple presentation. Take a listen. So as I've already introduced us, so I'm Darlington, and our supervisor is Professor Roman Shaw of the University of Calgary, and we want to show you what we've been doing the past 8 months on the Drillbotics Group A project. So Reza, take it on.
Okay. With the agenda, we have first directional drilling concepts about well trajectory and drilling simulation flowchart. And then we go through the torque and drag analysis, definitions, why we need torque and drag analysis, buckling limits and tensional limits, and inputs and outputs data of torque and drag calculations. And at the third part, we have dynamics mathematical model and offset controller, ROP compositions, ROP calculations, azimuth minimum curvature method, and go through the measure depths, weight and width, and RPM control system, and plan paths.
All right, thank you.
Yeah, for a directional drilling concept, we have different type of reaching the target. For example, we have build, hold, and drop, and the other one is build and hold. The other is continuous speed, and we also have the horizontal directional drilling. Usually, for directional drilling, they use mud motors, and they use the rotary stable systems too. But it depends on the decision of the operations. They decide which one will be used for the directional drilling. Our program is program for both of them, and we can use the RSS or mud motors in this competition. Well trajectory. In here, we can say that at first, when we want to reach a target, we have a well path. Here we have the proposed well path with the purple color, and you can see that with the actual well path, we are trying to reach the target when we reach out of it. So with just some sliding mode, and then we have some rotation with the mud motors, or changing the direction with the RSS, we can change the direction and come back to the actual well path. Darlington, you can continue.
All right, thank you. So for the Drillbotics competition, we designed this flow chart to show how we start our simulation and what triggers a stop, or at what point the simulation comes to an end. So I'll just zoom into this flow chart for you to understand basically. So obviously we're going to be given some targets, and with those targets, we're going to initiate our initial inclination, azimuth, and measure depth. Obviously, they all start at zero inclination, 0 azimuth, and 0 measured depth. And then for each step, we're going to have a planned in a next inclination and plan next measured depth based on the original well plan. So when we get that those targets from the Drillbotics committee, we're going to design a plan path to those targets, and then those plan paths would be repeated as we run the simulation every new step. So to go from one inclination azimuth to the next one, we're going to calculate the side force and steering force needed, and then based on that, we're going to calculate based on the forces calculated, imputed on the BHA. We will decide what is the next. We'll calculate what the next azimuth and the next inclination is, and the next measured depth based on the BHA and rock properties. So with those calculations, we will know if our actual path is far away from our planned path, right? And obviously the operation parameters in every step will be calculated based on the weight and bid, RPM and ROP calculated. We'll do all that using some control system and checking some safety values, making sure that every step that the buckling limits and all the other limits are not exceeded. And then obviously, every time we do those calculations, we will impute the azimuth, the inclination, and the measured depth into the minimum curvature method and calculate the actual northern, eastern, and TVD and store those values in our app as the actual part, right? And then obviously we're comparing all of that with the planned part. So at every 100 feet, if that's what is given to us by the robotics committee for new surveys, if it's every 100 feet they want it, or every X feet, we will see if we are at that point. For the mud bottle method, we'll be checking if the planned part is the same with the actual part. But for the RSS model, at every simulation step, we are checking if the planned part and the actual part are equal. So depending on that, if it's not equal, then we'll go back to the previous step to calculate the forces that can take the beat back to where the planned part is. If it's equal, then we'll continue until the simulation stops. But if we're having some issues while simulating in terms of twist off and all of that issues, it could lead to the simulation stopping, that the well we couldn't drill to target, or if our control system is able to correct it quickly enough, then we continue simulating until we get to the actual targets of the simulation. So that's the summary of the flow chart for our simulation. Now, one of the backbone of our simulation is torque and drag analysis. And as you know that the torque is applied at the surface, creating an RPM, and that torque is expected to be actualized at the beat. But obviously, we are going to have torque losses and side forces as we'll drill down the hole. And that means that the torque at the surface will not be equal to the downhole torque. There will be losses. So all of that are very important, because we have torque limits, and based on those torque limits, you want to make sure that you're not exceeding the torque limits or of the components, right? So those torque and drag analysis are important, and as well as we're pulling and as you're pulling and lowering your drill string, obviously there are going to be drags that are occurring, and we are doing some calculations about those drags while doing our simulation. And so why we need torque and drag analysis basically is to make sure that the drill string design is done to reduce torque and drag. So in these cases, is autonomous drilling. We already have some BHA components behind the scene, but we will make sure based on the plan, the targets given to us, that the drill string design is done with the initial. So there's a torque and drag analysis done with the planned part, and the BHA components that are used will not exceed the limits that we have for torque and drag, and making sure that we are monitoring the friction both for the pulling and for lowering, right? And so the basic concept here is that whilst we're doing the torque and drag analysis, is to ensure that while drilling, the buckling limit on the compressive force side is not exceeded, and the tensile limit on the tension side is also not exceeded whilst we're drilling. So that safety window, we'll always be checking that in our simulation to make sure that we are in that safe window, and that's the only way we can drill, right? And so you notice in this case that if we have a scenario where we are extending that scenario, we're going to buckle. And if we continue buckling, we cannot continue drilling, right? So obviously the simulation will stop at that point. So those are very key facts that we want to take note of, even the tensile limit as well. So yeah, for torque and drag analysis, our input information is going to be the well part data, the drill string components, and of course the operations data and hole condition. But if at any point, especially at those survey points, if we notice that there's the actual part, then the actual map of the torque and drag analysis will be updated with what the new actual part is, because obviously the torque and drag analysis will be done with the planned part initially, but as we drill and get to survey points in the mud motor method, we'll update the torque and drag plot. And that plot will be updated every simulation step for the RSS model, depending on what the robotics team is requiring of us. The output data basically would be the hook load, surface torque, and then that measured depth versus hook load plot and measured depth versus surface torque plot All of that will be showing in our app on the day of the competition, just to make sure that we are able to see that we are not exceeding those limits, and that we are considering, we are understanding what the frictional factor is as we're drilling all through. So now I'll pass it over to the other team members. I think Ray to present this part. Thank you.
Yes, so now we are moving on to the dynamic mathematical model. Now we're beginning with the weight on bit and the RPM control system. So this system takes in the user input. We can see in the diagram that we have a controller, plant, and these two are governed by the top drive AC motor for the RPM and a simple mass spring damper system for the weight on bit. I have also implemented a direct method for this one to discretize them so that we can use sampling periods in our simulation. On the left-hand side, we can see the governing equations for the weight on bit, and on the right-hand side, we can see the governing equations for the RPM. And moving on to the next slide is an example.
Thank you.
So moving on to the next slide is an example of how the user input is going to be different to the actual weight on bit and RPM values. And this is what we expect in reality, because even though we supply it the user desired weight on bit and a desired RPM, in actuality, we will have different values. These actual values could be lower or more than what is expected due to losses. And these actual values are what is supplied to the simulation every iteration to provide us with the next important values. Moving on to the next slide. This is just a flowchart of the dynamic mathematical model, and we'll continue more on this.
Okay, so this is the dynamic mathematical model so that we come up with our new inclination, new azimuth, and new measure depth for the directional drilling. We will start off with a well-planned design based on the target point. And then we gonna have an offset controller running through the system, running through the plan in order to get the offset azimuth and offset inclination. From there, you'll be able to get the F-bit offset caused by the RS, and from there you get the RP azimuth and RP inclination. RP ratio is affected by the weight on beat, and from there, some of the important properties or parameters can be calculated, like the northeast and the true vertical displacement. Moving on to next slide.
One of the initial steps after being supplied with the target points is to first define and calculate the planned well path. And as such, it has been said in the previous slides, this planned well path is very important because we need this to be compared to the actual location of the bit at any current point in the simulation. And the difference between the current position and the target position will tell us how much side forces we need to steer back the bit into the correct direction and correct position. Moving on to the next slide, we also use this same equations to calculate the kickoff point of the actual simulation itself. We can see that it is based on the mathematics of a chord on a tangent. The step begins by calculating the build rate needed to arrive to a target position, and we also calculate the radius of the turning. And from those two things, we can therefore calculate the horizontal displacement as well as the vertical displacement of the bit, which tells us information about the correct kickoff point that is most optimum for us to hit all of the targets that we have been provided. Moving on to the next slide, we have the offset controller.
So the offset controllers control the direction of the drill. So we will set a certain maximum limit that the offset can reach, which is directly proportional to the dot severity. So if the difference between the target point and the current point would result in a larger DOS than what is required, it can only reach that maximum offset, can go any further than that. Otherwise, the offset will be adjusted accordingly based on the difference of the target and current points. So moving on to the next slide. We have in our simulation, as you can see, we start out with input the current point and the target point, inclination and azimuth. And from there, you calculate the difference between the target position and the current position. If it go over the max limit, it can only go to the maximum offset, which is so the max off variable will vary from 0 to 1. If the target position minus by the current position is less than the maximum limit, it will be adjusted as this equation right here, which is offset equal to 1.5 multiplied by the absolute value of target minus current multiplied by max off. From there, you'll be able to find the offset inclination and offset azimuth. Next slide.
The output of the previous controller, which is the azimuth offset and the inclination offset, will be used to calculate the side forces that will steer the bit. It is directly proportional to the offset normal, as well as the elastic modulus, the moment of inertia, as well as the correction factors for the horizontal and the vertical position of the bit. These will provide us with the F double prime offset, which is the inclination force, and as well as the F prime offset, which is the azimuth force. These are going to be our steering forces to direct the bit to the correct position. Moving on to the next slide.
Okay, so the rate of penetration condition is divided into 3 components, which are the RP axial, RP inclination, and RP azimuth. RP axial is mainly driven by the weight on beat. RP inclination changes the inclination of the bit, and the RP azimuth changes the rotational angles of the bit in northeast Cartesian coordinate. The RP calculation is as follows. Next slide. As you can see, the RP inclination and azimuth is directly affected by the bit offset, which is the side forces caused by the RS system. And the RP axial is mainly affected by the weight on beat. Moving on to the next slide. With the calculation of RP, the inclination, measure depth, and azimuth is updated after every period delta t, which in our case is defined as 5 seconds. This is the model of inclination. As you can see, the arc tangent of the RP normal divided by the RP axial equals to the angle RP, and it will be used to calculate the next inclination. So next we have the measure depth. So the measure depth is the actual distance that the drill has drilled through. The resultant forces drive the measure depth the resultant force drives the measure depth of the bit. The resultant force is composed of the weight on the bit and the forces coming from the RS. Move on to the next slide with the azimuth. The azimuth model was modeled the same way as inclination. However, it does not have to start from 0. It could start with the design angle at the kickoff point. So yeah, moving on to the minimum curvature method, and Darlington will please keep presenting.
All right, thank you. So with the minimum curvature method, you can see that we're taking inputs like the measure depth and the inclination and the azimuth, right? And the RF factor. So with these inputs, we're able to calculate the total vertical depth, the northern and the eastern, as I said earlier in our flow chart. So with that, that's what we now eventually plot to compare to what the planned path is. And we can know how far off we are from the planned path. And if it's a little bit far, we can also go back in the simulation to recalculate the planned path, right? So the actual plot to try get the force that will make it get back to the planned path. I really want to say that the team has worked very hard, and coming from very low or little to low knowledge in the drilling industry to this point where we're all able to present and understand and be able to implement our ideas for autonomous drilling rig. We are very grateful to the Drillbotics team for giving us this opportunity to learn. And we have gone through lots of references over the past couple of months. And yeah, we look forward to the competition itself next week, Tuesday. We'll have a fantastic app to show and fantastic results, hopefully. Thank you so much for listening. And from myself and Reza and Ray and we say see you next week. Bye-bye.